Hello friends, welcome to this dimensional analysis class. In this class, we'll learn a lot. We'll learn basic concepts, we'll learn dimensions of three fundamental constants, we'll learn dimensions of mathematical functions, we'll learn dimensional analysis on simple pendulum, we'll also learn dimensional analysis on Planck units, we'll learn dimensional analysis on atomic bomb blasts, and on fluid dynamics, and on electricity magnetism, and we'll solve and get ideas of some PYQs of JEE Advanced and some PYQs from CSIR NET and JEST. So let's begin with basic concepts. We all know that we have 7 fundamental quantities which are mass, length, time, temperature, current, the amount of substance, and luminous intensity. We all have their units. These are SI units. You know, these are the basic symbols: M, L, T, theta, A, mole, and candelas. I guess you know this. So the first concept is the dimension of both sides of a physical relation must be same. If you have a physical relation, suppose A equals to B, then the dimension of A and dimension of B must be same. Suppose you have your law of gravity. So in law of gravity, your dimension of force should be same with the dimension of the gravitational constant multiplied by dimension of two masses and divided by the dimension of length square. If you have an equation in a physical relation, so in each and every term, the dimensions should be same. Say if you have a relation S equals to ut plus half of at squared, it's very familiar relation. So the dimension of S should be equal to dimension of ut. This should be equal to the dimension of at square. That each quantity S, ut, and half of at square will have of same dimension. Suppose you have a derivative. What is a derivative? Derivative, say the velocity is the derivative of position, dx dt. That means, what does dx dt mean? Dx dt means a bit of change in x divided by a bit of change in t. So this is essentially a bit of x divided by a bit of t, delta x, delta t. So dimension of v must be same with dimension of x divided by dimension of t. This is delta x by delta t. So that's why the dimension of derivative, which is v, should be equals to dimension of x divided by dimension of t. Using this, you will calculate dimension of lots of quantities. So dimension of velocity, what it will be? It will be L by T. Dimension of length, we write it by abbreviation L, and dimension is always written as in capital letter. By dimension of time, time is written as T. So it is L by T, and we write it like this, L T minus 1. In general, if you have any derivative, A is df dx, the dimension of A will be dimension of f divided by the dimension of x. That's it. Application. Say acceleration. Acceleration dimension will be the dimension of length by time square. Why? Because acceleration is derivative of velocity itself. So velocity have dimension of length by time. So acceleration will have the dimension of length by time square. So L t minus 2. Dimension of force is very simple. It's force is generally mass into acceleration for constant mass, of course. So that will have dimension of mass multiplied with dimension of acceleration, and this will be, acceleration is L t minus 2. So this will be ml t minus 2. Dimension of energy is force into distance. Energy is defined like this: integration of force over distance. So it is just dimension of force multiplied by dimension of distance. So there is another L adds up to with force. So it will be ml square t minus 2. Very simple. These are very basics. What is the dimension of Young's modulus? Young's modulus is defined as stress by strain, and stress is pressure, force by area, and strain is the ratio of the length increased by length itself. So strain is delta L by L, and this pressure is stress. And see, delta L by L will not have any dimension, because delta L is bit of L and L is L. So that L cancels out. The dimension of L cancels out. So dimension of Young's modulus will be dimension of pressure itself, because this thing does not have any dimension. So this will be force by area, the dimension of pressure. And force, I already know that dimension of force is mLt minus 2. And if we divide with area, area is just length square. So L to the power minus 2 will come. So it will be mL minus 1 t minus 2. As simple as that. So finding dimension of a quantity is not that tough. All you just need to know what is that quantity. So I know what Young's modulus is. That means I know what dimension of Young's modulus will be. Okay, so Young's modulus dimension is same as pressure. That does not mean that Young's modulus is pressure. This is something else. So two quantity may have same dimension, but they will represent completely different things. We have lots of quantities having same dimension, but they are essentially different. Let's go to another thing, which is finding dimensions of three fundamental constants. Okay, so what are these three constants? We defined the three constants. One is G, which is Newton's gravitational constant. Second is H, which is Planck's constant. And third is C, which is essentially the velocity of light in free space. So let's say what the dimensions of G, H, and C is. Law of gravity is simple. F is g m1 m2 by r square. So we can find dimension of G from here. So dimension of F must be equals to dimension of G multiplied by dimension of 2m divided by dimension of L square. So it's mLt minus 2 equals to dimension of G. 2 m's we have, so m square, and 2 L's we have, so L square. And that is divided by, so that says L to the power minus 2. And just equate just a simple algebra to see that the dimension of G will be m to the power minus 1, L cube, and t minus 2. That G will be there, m goes here, so m power reduced by 2, and L's power increased by 2. That's it. Planck's constant comes from Planck's law. So this you might not know right now, or you know it. This is Planck's law, which tells you that energy in a very subatomic scale, in a very small scale, is quantized. And if you have a wave with frequency nu, so the very basic quantity of energy, basic quanta, that energy will be h multiplied with nu. So that gives you h as a constant. So what is the dimension of this? We need to equate the dimension of the relation. So dimension of energy is left side, and right side dimension of h and dimension of nu. Nu is frequency, so frequency is 1 by time. It is written as unit hertz. So it is h t minus 1, and left side energy is ml square t minus 2. Just a simple algebra to see that h dimension is ml square t minus 1. These are all easy mathematical functions. That is maybe slightly confusing. Say if you have some quantities, e to the power minus kx, e to the power minus ax square, or e to the power minus h omega by kbt. So all these things which are inside that exponential, this minus kx, this minus ax square, and this minus h omega by kbt, they do not have any dimension. Why is it so, sir? Why this minus kx will not have any dimension? We can answer the question in many ways. For now, it is sufficient for you to know that if you take derivative of e to the power minus x, you get e to the power minus x itself. So then think about it. Just think about dimension of derivative of these quantities, and then just think that why this should not have any dimension. If minus kx have any dimension, then e to the power minus kx will also have dimension. By taking derivative and equal and make sense that if you take a derivative of a quantity df dx, the dimension of df dx will be dimension of f divided by dimension of x. And then think logically that why this should not have any dimension. You need to think. If you want to learn, you need to think. you need to work out. So think about it. I'm giving you as an exercise, and tell me in the comments that what your logic is, or you can email me. My email is always given there below in my every video. So okay, let's form a general rule that if you have e to the power, that minus is not required. If you have e to the power any function, e to the power fx, that immediately tells you that fx should be dimensionless. Work it out, think it out why. If you have any function inside, you always have functions inside logarithm, inside sine, inside cosines, all this kx, ax, and bx, all these quantities will not have any dimensions. Once again, think about it, work it out, email me, comment. All this fx, any fx inside any logarithm, sine and cosine, these fx are dimensionless. This concept is very much asked in JEE questions. So if you are JEE aspirant, so please keep in mind of this. Okay, dimensional analysis on simple pendulum. This is first problem you will encounter to do dimensional analysis on. So let's say you have a simple pendulum. Pendulum have length L. The mass of that pendulum bob is m. And we have gravitational constant. Of course, the pendulum vibrates due to gravity. Otherwise, it will not. So we start a model. We think a model. In any dimensional analysis, you need to think a model. So that model is, my model is, choosing your model depends the success. The success of, the very success of your dimensional analysis depends very much on what your model is, what the dependent quantities you are thinking about. We are postulating that frequency of a simple pendulum will depend on mass of the bob, this mass, length of the thread, this L, and acceleration of gravity. Right? So after thinking model, we write it like this. Let's say frequency of your pendulum depends on the mass to the power A, L to the power B, and gravitational acceleration to the power C. Now, the combined dimension in right-hand side must be equals to the dimension of frequency. The dimension of frequency will be just 1 by time. Frequency is 1 by time. Gravitational constant dimension is just a dimension of acceleration. Sorry, this is not gravitational constant, this is gravitational acceleration. Gravitational constant is capital G. This is acceleration of gravity. So this is simple acceleration. So its dimension is mlt minus 2. So we just equate it. 1 by t, left hand side. Right hand side is m to the power a, L to the power b. L is length of the thread, m is mass of the bob, and g is L by t square, this to the power c. Now just do a combination of, just write m to the power, all equal, find all quantities where we have m, and m have appears only one time, so it's m to the power a. L appears 2 times, so here it's b, here it's c, so L to the power b plus c, and t appears only 1 time, so it's t to the power minus 2c. So t to the power minus 1 should be equals to this, and then simple law of exponents tell you that your a should be 0. Left hand side you don't have any m, so your a is 0. Left hand side you also don't have any L, so your b plus c will be 0. Left hand side you only have t, so here you have t to the power minus 2c, and here you have t to the power minus 1. Equate this two, that gives you minus 2c is minus 1. This is a simple algebra to verify it, that your answer is a equals to 0, b equals to minus half, and c equals to half. And your essential postulate was this will be m to the power a, the frequency will be equals to m to the power a, L to the power b, g to the power c. And you got that values of A, B, and C. Now, you just substitute these values, that your frequency depends on some constant. This constant cannot be evaluated by dimensional analysis. So there will be always a constant with this G and L with a square root. Why? Because L to the power B and that B is minus half by your dimensional analysis. And G is G to the power C and C is half. So that's why your frequency is K square root G by L. Time period, one full, the time required to do a full oscillation. This is inverse of the frequency, and you get L by G. And you know what the values of K will be in a detailed physical consideration. But dimensional analysis can give you exactly how this frequency depends on J, G, and L. The success depends on your model. These three quantities, if you had not properly selected, then you could not have an answer, proper answer. So for physical answer, choosing your model is essential. In the exam purpose, we always given the model. So not an issue, but in practical purpose, you need to select your model. Okay. Now, I'll tell you, there is another way to think about. This is essential for your future analysis. When you do your graduation, then you learn many more things about dimensional analysis. But for a school student, this is sufficient. We have four quantities to be considered in a pendulum: mass of the bob, length of the thread, acceleration of gravity, and frequency itself. Frequency depends on these three. You can also say mass depends on these three, or acceleration of gravity depends on these three, length of the thread depends on these three. That means these four quantities have a relation. You have written frequency at left and these quantities at right. You could have written L at left and all other relevant quantities at right. That is a simple algebra to do it. So in a generalized sense, I say there is a relation between mass of the bob, length of the thread, acceleration of gravity, and the frequency. You are not taught in this way, but you know the history of dimensional analysis. We started in this way. So I say that relation between them is unknown. So we need to find a relation between these four quantities. So we think in this way, that can you create a dimensionless quantity? Can we create a dimensionless quantity? Dimensionless quantities are very important in physics. You learn through your journey using dimensional analysis. Relation between these four is unknown. Can we create a dimensionless quantity using dimensional analysis? Okay, let's see. Mass, length, acceleration of gravity, and frequency of oscillation. Dimensions of all four quantities are known. So we can find it. It is not a problem. That we say the dimension of length of the thread by divided by the acceleration of gravity is nothing but 1 by t square. M does not appear in this. So okay, if we divide the dimension of length and dimension of gravity, so I get 1 by t square, and that directly depends on frequency of oscillation. So you got your answer right. The frequency of oscillation 1 by t square is equals to L by G. So your dimensionless quantity will be nu square L by G. Nu square has dimension of 1 by t square. So nu square is 1 by t square, and L by G have dimension of 1 by t square. So nu square by L by G, actually, I'm sorry, I written, no, I did wrong there. L by G is 1 by t square. No. I made a mistake somewhere. That G is below. Okay, so L by G is t square, and frequency of oscillation is 1 by t square. So nu square, dimension of nu square multiplied by dimension of L divided by dimension of G, this is a dimensionless quantity. this nu square L by G is a dimensionless quantity. So you have created a dimensionless quantity using these four things. M we didn't choose because M appears only once, so we could not accommodate M itself. So this dimensionless quantity can be taken a constant. This value of this quantity does not depend on any unit you choose. So this can be taken a constant. This is another way to do dimensional analysis. So we, let's say this nu square L by G is some constant. Let's say it's K square or anything. You might have chosen only K or only C or whatever you like. And using this, you got your relation, desired relation, nu is K square root of G by L. This builds up our foundation of understanding dimensional analysis, which will be detailedly explored in class 2. There will be a class 2. This is class 1. So we go to Planck's units. So Planck units are natural units, sometimes also called. We have already seen we have three interesting constants. One deals with gravitation. The Planck's constant h deals with quantum mechanics, and the velocity of c, it deals with special relativity. So my question is, these three pillars of physics and the very pillars of those branches are these constants g, h and c. So can we create some quantities with no dimension using this three constant? Because something with dimension depends on our chosen unit, and we choose unit depending on our experiences. Choice of units are human-centric, very much human-centric. So now my task is, so don't think about all the details right now, my task is to find some dimensionless quantities using these three constants. So first, can you create a quantity with dimension of length using these three constants? Sure. You just manipulate a little bit with these three constants, you get something with dimension of length. If you multiply h and g, divide by cq and take a square root, you will verify that we get some quantity with dimension of length. We call this Planck length. Do a Google search or ask ChatGPT to know what the numerical value of this is and what could be its significance. You can calculate the numerical value, right? You know the value of these constants. So do it. What is the numerical value? And what is the significance of this Planck length? And can we create something with dimension of time? Sure. We could have calculated with something with dimension of length. We can surely calculate with dimension of time, and which is essentially hg by c to the power 5. Length have c to the power 3. Time have c to the power 5. Square root hg by c to the power 5. This is Planck time. Again, do a search. Can we create something with dimension of mass? Sure. This is Planck mass. hc by g. You'll see the dimension of mass will be hc by g. Do this or verify all this. Something with dimension of temperature. To involve temperature, you need to involve Boltzmann constant as well. So okay, you use Kb. So Planck temperature, something with dimension of temperature involving these three constants will be this. So these Planck temperature, mass, time and length, these are essentially creating something with dimension of length, something with dimension of time, something with dimension of mass, and something with dimension of temperature using these three constants. So these units we generally called natural unit. So if you take your Planck length as unit length, Planck time as unit time, Planck mass as unit mass, Planck temperature as unit temperature. No, temperature have lots of other things also, but okay, think about it, what this temperature is. Okay, So we learned that. Verify it, please verify. Now we do a very interesting thing. Dimensional analysis on atom bomb blast. This was real. This was very real. This is Trinity. Oppenheimer named this Trinity the first nuclear bomb test. What happened here? The bomb got boom. Then an intense shock wave of air created. Shock wave. Boom. Lots of energy released. This wave, the shock wave, burning of the oxygen present in the atmosphere, that is picturized by this fire. So we call it, this is a, let's say it's a shock wave of air, that fireball. It have radius r at time t after the blast, because that fire was visualized and captured by camera. So we got 3-4 pictures just after some milliseconds, 15 millisecond, 20 millisecond, 30 millisecond, like this. So this picture have is taken just after 0.025 second, that means 25 millisecond after the blast, and that blast already have radius, a big radius, maybe 200 meters around. So this picture only we have. Say you are a future scientist, so let's say I give you this picture and tell you what the picture is about. I already told. Using this only, can you, we give you two data, say after 15 milliseconds, this is 25 millisecond. Let's say we have another picture. In reality, we have another picture. So you can use 225 also, no issues. So if you say after 100, after 15 millisecond, we got 100 meter of radius of that blast. That data from photo you have. And the burning air density approximately is, let's say, 1 kg per meter cube. This is atmospheric data. You don't need to have access to any detail. So this picture you have, this data you have. You can use 200 meter and 25 millisecond, no issues. Just using this data, can you estimate the blast energy? How much energy was produced in that blast? Can you? Let's think. And if you estimate energy, can you estimate how much uranium was converted into energy in this blast? This was done in reality at 1949, and the data was so accurate that the Manhattan Project, the US guys thought that their data has been leaked, their data has been breached, but that calculation was done by brilliant physicists. So let's say what quantities we have here. We have the radius of the shock wave, that radius. This is one quantity. Density of air, shock, boom. Some blast, that means some energy released, created, blast in the air. So density of air is very important quantity here. So it is rho. The dimension of this radius is L. The density of air is rho. The dimension of density is m by L cube. Sorry, m by L cube. This is m L to the power minus 3. Most important data is time. How much time we have got that radius. So time is an important quantity, and blast energy. We have this quantity, which I need to find. So this 4 quantity, and with that dimension, using this dimension of this 4 quantity, you see, everything depends on my model. What data we have, you successfully identify, you need to identify that density of air will be a relevant quantity. If you identify this, then you can proceed. Otherwise, your answer will be wrong. The density of air will come into factor here. The time, energy, and radius, of course. So if you have successfully identified these 4 quantities, so then you can easily see that energy will be related by r to the power 5 multiplied by rho by t square. You just do it. This is a simple homework to see that. And this r to the power 5 rho by t square is mlq by t square. So mlq, ml minus 3 t minus 2 here. And to get it there, you multiply it by L to the power 5. Otherwise, that L to the power 2 will not come. So then this relation you have using just simple dimension analysis. And if you take this constant to be 1 for the time being, let's say, then you estimate your energy is approximately 4 into 10 to the power 13 joule. This was almost, and your mass which was converted to produce this amount of energy is just E by c square. E is mc square, Einstein. So here you got your mass is 0.5 gram. That amount, this is very close to real data. Just 0.5 gram of uranium was converted into energy in this first Trinity blast. In recent days, people have methods to convert 1 kilogram of uranium into boom. So you can think about how much big the impact will be. So, okay. This Trinity dimensional analysis is generally called the greatest problem of dimensional analysis, or the greatest problems solved by dimensional analysis ever. Now we proceed to one very simple problem in fluid dynamics. It's generally called Stokes' law. But before, we need to find the dimension of eta. This is viscous force per unit area. This is A by A. It is, you know the relation, right? The force gradient is equals to the coefficient of viscosity eta multiplied by velocity gradient dv dx. dv dx is how much velocity changes with a bit of x, with unit x. So dv dx is velocity gradient, the change of velocity in a fluid. We are considering a fluid, right? The fluid flowing inside a pipe. And this is just force by area. So you just write the dimension of both sides. So force is mlt minus 2, area is L square, eta is unknown, and velocity is lt minus 1 and x is L. So it's a simple algebra to verify that eta will be ml minus 1 t minus 1. Just you do it yourself. Maybe anytime you can pause the video and get your answer, and then once again play that video. Okay. So now proceed to Stokes' law of viscous force. So let's say we have a spherical body of radius r moving with a terminal velocity. What is terminal velocity? Terminal velocity is if you drop a ball in a viscous liquid. In first you do an experiment. You may do an experiment with the oil, but okay, you may paraffin oil also, anything. So after a few seconds, the velocity will increase, and after that, the velocity will be constant. Will become a constant. That constant velocity is called the terminal velocity. And the liquid, the coefficient of viscosity of the liquid is eta. What we are trying to do here, we're trying to estimate the resistive force due to viscosity. Of course, any liquid will give you a resistive force. If you drop a ball inside a liquid, that liquid will of course produce a resistive force. We're trying to estimate that resistive force. So due to the viscosity of the fluid using dimensional analysis, we need to build a model. What are the parameters? The parameters are r, v, and eta. R is the radius of the ball, v is the velocity, terminal velocity, and eta is the coefficient of viscosity. After you given the parameters, the work is 5 seconds. We just equate it. forces equals to k r to the power l. K is a constant. Eta to the power b, and let's say v to the power c. The dimension of eta I already told you, m l minus 1 t minus 1. So just write L here, L to the power A. Eta is this, M, L, T. So we all have to the power beta here, B, L to the power minus B, T to the power minus B. And there is velocity. So L to the power C, T to the power minus C. So now do this in the same method, proceed by similar method as in the pendulum itself. So this is m to the power b. M appears only once. L to the power a minus b plus c. Okay. T to the power minus b plus c. Just verify it. So now equate the power m, power L both side, power T both side. So that simple algebra give you A equals to B. That means B is 1. A minus B plus C is 1, minus B minus C is minus 2. So that simple algebra, do it yourself, give you A equals to B equals to C equals to 1. All the ABCs are 1. So if all the ABCs are 1, in our model, I started with this, that force would be equals to this. So if all the ABCs are 1, then your force is K, R, eta, V. K is some numeric constant. So that gives you the dependence of two variance of, dependence of ratio of the two forces in two different conditions, R1 eta 1 V1 by R2 eta 2 V2. So these are the algebraic problems you need to solve sometimes. So we can solve many problems in this way. Many problems. There are separate books of dimension analysis itself, which considers hundreds of problems. These types of problems were generally properly written by Lord Rayleigh around 1914, I guess. 1914, 1916. In this time, all this structure of dimensional analysis was built. So, okay, we proceed with, we are almost finished. We are almost done. So, we will just do some dimensional analysis on electricity and magnetism, and I will give you some problems, PYQ problems as a homework. So let's be with me. So this is dimensional analysis in electricity and magnetism. This is very simple. What is the dimension of epsilon naught? We once again start with Coulomb's law. In Coulomb's law, we have force is equals to 1 by 4 pi epsilon naught. This is a constant multiplied by two charges divided by the distance square. So that means dimensions, equal dimensions of both sides. So force have mlt minus 2, this epsilon naught have some dimension, we don't know yet. Q1, Q2, we write Q as A into T. A is ampere. We are considering A as a fundamental dimension here. In some problem, the Coulomb itself is taken as fundamental constants. So don't worry about it. In general convention, we take ampere as more fundamental. But okay, in my opinion, Q should have been more fundamental than A. So, okay, it depends on what your question is. Means what the paper setter assumes. But in general convention, we take ampere. So Q is ampere into time. L is R square. So that's it. You equate the dimension of LHS and RHS. Dimension of 4 pi does not have any dimension. So take this epsilon naught here. So you see that dimension of epsilon naught will be A square. Bring all this at right hand side. So that will be the dimension of epsilon. This is simple. Very easy. What is the dimension of electric field? Once again, we start with the Coulomb's law. Forces QE. We just equate dimension both sides. MLT minus 2 is ATE. Then you get dimension of electric field. So in this way, you can find dimension of anything. You should know that, right? If you don't know what Coulomb's law and what electric field is, then you don't understand. But I assume that you are either an undergraduate student doing BSc or MSc or advanced JEE student. You already know the basics. I'm not assuming you're you just started class 11, then this lecture might be hard for you. Okay, let's go to calculate the dimension of magnetic field. Here we start with Lorentz force law. There's a Lorentz force law which gives you the force of a particle which are moving inside an electric and magnetic field. So then each term of that equation should have equal dimension. That means dimension of force should be equal to the dimension of Q into E, which we already used here. And if we have magnetic field, here we don't have magnetic field. That's why that B is not appeared here. But if you have a magnetic field, the force becomes QE plus Q into V cross B. So we consider the second term to calculate the dimension of magnetic field. So the dimension of F should be equal to the dimension of Q multiplied by dimension of the velocity multiplied by dimension of magnetic field. So that's it. That gives you your dimension of magnetic field as m t minus 2 a minus 1. Just if you are confused, you have a pause here and just do that algebra yourself. So in this way we can calculate the dimension of magnetic field. We can calculate the dimension of mu naught by considering the simplest expression of magnetic field for infinitely long current. If you have an infinitely long current, your magnetic field is, you already must know that, mu naught I by 2 pi r. So this expression equate constants, equate dimension, both LHS and RHS. So dimension of B is equals to dimension of mu into dimension of current by dimension of L. Simple algebra give you the dimension of mu is mLT minus 2 a minus 2. You don't need to remember the dimension of everything. You cannot and you should not. What you need to know is how to find dimensions of any quantity if you know the physical relation. So you focus on the physical relations itself. Remembering everything is not a good way to learn. It's not a very efficient way to learn. That makes you inefficient. So try to learn things, not try to remember things. Okay. You can calculate dimensions of many more quantities in electricity magnetism. So try with it. Dipole moment, resistance, capacitance, magnetic flux, inductance, Boltzmann constant. These are from thermal physics. Boltzmann constant, thermal conductivity. Only if you know what these quantities are. If you don't know, if you are just starting class 11, don't calculate all this. You just focus on basic mechanics. You learn Newtonian mechanics. Slowly you will learn to calculate all the dimensions because you will learn all the relations. You will learn the definition of dipole moment after some time. Then you calculate it. Right now, you don't. Okay, guys. Some PYQs from JEE Advanced. Why not from JEE Mains? Okay, this is just a single video. Mostly focused to more advanced guys, CSIR NET and JAM aspirants. But okay, these JEE Advanced questions are good to practice both for all level of students, both for school and college and university students. So let's do some PYQs, some interesting PYQs. I should have written some interesting PYQs. This is a very common question, initially asked in 1997, and it's now part of every homework in every book. That if you have a gas equation, pressure plus some constant by P square multiplied by some velocity, some volume minus some constant is equals to RT. This is an equation of real gas. So you know what PV and T are. The dimension of the constant A and B. What is the dimension of constant A and B? We have a dot there. Sorry, can I get a space? No space it's allowed. Okay, you can do it yourself. No issues. How? So A by V square A by V square should have dimension of pressure, because you can add something of dimension pressure only with pressure. And here the B must have dimension of volume. Why? You're subtracting B from volume. And you can only add or subtract something with dimension of volume with the volume. You cannot add something with dimension of pressure with the volume. You cannot add something of dimension of energy with volume. You can only do it dimension of volume can be added with volume. So that B have dimension of volume, and A by V square, B is volume, here B is volume also. So A by V square should have dimension of pressure. Then do it. Tell me the answer in the comment box. This is the similar question. This question is still asked in this type of question is still asked in JEE, both mains and advanced. What is the dimensional formula of beta? This is pressure. So what you do? See, if I have e to the power minus alpha z by k theta. So anything inside exponential should be dimensionless. Anything inside exponential should not have any dimension. So my alpha z by k theta will not have any dimension. So e to the power, this whole thing does not have any dimension. So alpha by beta should have dimension of pressure, because pressure is at left side. Right side we don't have this e to the power. This part does not have any dimension. So only we have alpha by beta. So alpha by beta should have the dimension of pressure, because RHS we have pressure. So do it. Alpha z by k theta, you get your dimension of alpha, and then alpha by beta is dimension of pressure. Do it yourself. I don't just give you a solution. If you want to, if you still cannot, I refer a very good book. After a few minutes, all problems are solved there. But first try. First again repeat the lecture, whatever concepts I have gone through. Then you attempt again. The PDF of this whole lecture slide will be available in my in the description itself. So don't worry about it. This is, I think we already done. JEE Advanced 2015. This Planck's constant h, speed of light, and gravitational constant g are used to form a unit of length and a unit of mass. Then the correct options are, we already know that. We've done that. Planck mass, Planck length. Remember? Planck length, Planck time. So something related with this three constants and this Planck mass, Planck length, Planck temperature. This question asked. If you go through the JEE mains and advanced papers, you will get many questions related with this concept. Natural units, it's called. Okay guys, this is a very interesting problem, kind of a research problem. Okay, so okay, I am sorry, this is, we have a printing mistake here. I'm sorry, we got a printing mistake, I guess. This is not epsilon naught. Just give me a second. Okay, I got that. This was not omega 0, this was epsilon naught, and this was epsilon naught. This is NE square. Okay guys, now look at that problem. N be the number density of free electrons. Okay, number density. How much number of electrons have in unit volume. That's why number density, not number. electrons have mass m. Each electron have mass m. Electrons are placed in an electric field. They displace slightly from the positive ions, of course. If you have an atom, we have a nucleus, core nucleus with positive charges, and a periphery electrons with negative charges. So if you place an electric field, so both will go in opposite direction. So there will be a separation between the positive charges and the negative charges. So then if you remove that electric field, the electron will begin to oscillate. Think about the situation. Your thinking capacity will be increased. So after the electric field is removed, the electron begins to oscillate. That oscillation frequency is called plasma frequency. You don't need to know anything else about it. Just read the statement. What it asked is to find the correct expression for omega p. The plasma frequency, we need to find the dimension. So it's a simple dimensional analysis to find the answer, because what I need to find is the correct expression for omega p, and that omega is nothing but a frequency itself. So my task is, which among these four quantities have a dimension of frequency? All four quantities have different dimension, and this should be E epsilon. All these four quantities have different dimensions. N is number density, number by volume. Number itself doesn't have any dimension. Mass is mass, charge is charge, and the dimension of epsilon naught you already calculated in this video itself. So use it and find the answer. Tell me in the comment. This is a very easy problem, I should say. A signal. The distance, a signal. You just make a pause and study the problem. We have a railway signal there. So we need to find out the visibility distance of a signal in a foggy condition. And we say that, say distance, you cannot see a distance from 1 kilometer away, right? You see a signal, say around 100 or 200 meters away. So that distance I need to find with dimensional analysis. So I need to guess how, among what conditions that visibility of signal depends on. So your model is the signal depends on the mass density of the fog. Of course, it's a good quantity, valid quantity to be considered. Intensity of the light, of course, the brighter the light is, the more visibility I should expect. The intensity of the light and its frequency. Of course, frequency have some relation with visibility. It should have. From your basic optics knowledge, you know that. Red light appears more, blue light appears less. So the frequency of light, the intensity of light, mass density of the fog. You consider this, do a dimensional analysis problem, what we have learned in the lecture itself, and find the D depends on s to the power 1 by n, and find the value of n. Do it yourself. It's a very simple problem. Say 5 lines of problems. This is Young's modulus using Planck's constants. Planck's constant, gravitational constant, and speed of light. Young's modulus is pressure, means the dimension of both are same. So using this G, C, and H, calculate something with dimension of pressure. You can do it. 5 lines of problem. JEE Advanced problems are slowly becoming less tough. the peak standard, say from 2010, 2014, that time of JEE Advanced. So before COVID, JEE Advanced problems were tougher. Right now, JEE Advanced problems are easier. It is evident from this 2024 problem I have also seen, not included here, left you as a self-learning exercise. The problems are getting easier day by day. This is also can be done, not a problem. Length. A length scale depends on permittivity, Boltzmann constant, absolute temperature, number per unit volume of certain charged particles, and the charge itself. So, which of the following quantities is dimensionally correct? That means you need to calculate something with dimension of length with all these quantities: n, number per unit volume, temperature, Boltzmann constant, permittivity, and charge. All the four options have different dimensions. Of course, it should have. So you play with this unknown. You play with these unknowns, dimension of everything you know by that time, and calculate. Try to form something with dimension of L. Entirely simple algebra. This is also a very simple problem. A physical quantity can be expressed in terms of electric charge, electron mass, Planck's constant, and Coulomb constant. So in this four quantities, with respect to these four quantities, calculate the dimension of magnetic field. So you equate the dimension of magnetic field with e to the power alpha, whereas E is the charge, m to the power beta, m is the mass of electron, h to the power gamma, and k is 1 by 4 pi. Sorry, this is epsilon naught. So this ignore. That's it. Equating all this, you find alpha, beta, gamma, and delta, and just find the value of alpha plus beta plus gamma plus delta. So I am not finding anything tough in this JEE Advanced problems. All the BSc MSc guys do also practice them. At least the problems what I am giving in the slide. For the JEE guys, if you want to practice all the PYQs, practice from this book. This is a very good book. I myself have this book in a physical form. So do this. CSIR NET JEST problems are easy, very easy. Easier than the JEE Advanced problem, I should say. This is just Planck's constant, Planck's length. Already solved it. This is Planck's temperature. We solved it. This is the nuclear explosion problem, Trinity atomic blast problem. We already solved it. So these are the types of problem dimensional analysis we can expect on CSIR NET. Sometimes we need to apply dimensional analysis in some other problems, because using dimensional analysis, getting the answer might be easier. Because you might have four different options, and the dimension of the dimension in four quantities are different, say. So you can just verify your answer with the dimensional analysis itself. So we'll learn the trick later also. Don't worry. What we will learn in the next class. This is the first class we have learned. Next class we will learn many interesting things. The advanced class, specially designed for CSIR NET students. JEE students also can attend, no issues. In the next class of dimensional analysis, we will learn Buckingham pi theorem. This will be very interesting. We'll do dimensional analysis on differential equation. We'll take Schrodinger equation as an example. We'll do dimensional analysis on integrations. This part in JEE students might need. This parts they may not need. That's it. So okay guys, so that's all for today. I'll likely to upload the next class within 1 week at most. Thank you so much for being with me.